Have you ever stopped, just for a moment, and wondered how long it would really take us to reach the far edge of our cosmic neighborhood? To travel from the warmth and familiarity of Earth all the way out to Neptune, that pale blue world drifting in the dark. I mean, not in the abstract way we sometimes think about space, as dots on a textbook diagram, but truly wondered. How many mornings would rise and fall on Earth while we were still on our way? How many generations might be born, grow old, and fade into memory while a single spacecraft continued its silent journey outward? You see, Neptune isn't just far, it's a lesson in scale. It sits so distant that light itself, the fastest thing we know, takes hours to bridge the gap. And that's the thing. When we talk about going there, we're really talking about confronting the true size of the solar system, and perhaps our own patience as a species. We're used to speed now. Messages cross the planet in seconds. Journeys that once took months are done in hours. So it's tempting, I suppose, to imagine that space travel works the same way. That with enough power and clever engineering, we could simply point ourselves at Neptune and arrive in something like a reasonable time. But the universe doesn't bend to our expectations. It asks us to slow down, to measure distance not in kilometers alone, but in years, in effort, in endurance. And when you begin to think about it like that, Neptune becomes more than a destination. It becomes a mirror, reflecting back our ambitions, our limitations, and our deep curiosity about what lies beyond the horizon of the known. Before we go on, I'd like to ask you to subscribe to the channel and leave a like. My aim here is simple: to help you drift off to sleep while exploring the wonders of science. Where are you on the map? Let me know where you are in the world and what time it is in the comments. It's always fascinating to see who's joining us from all around the world. So let's continue. When we imagine Neptune, well, you see, we often picture it as a distant blue dot, calmly circling the sun at the far edge of a tidy diagram we once saw in a schoolbook. But that picture, comforting as it is, quietly lies to us. Because Neptune is not simply far away in the way a distant city is far away. Its distance is not fixed, it breathes. It stretches and contracts as it moves along its long, elegant path around the sun. And as Earth, our own small moving platform, traces its much tighter orbit closer in. And that's the thing. When we ask where Neptune really is, we're forced to abandon the idea of a single number, a single distance, and instead step into a living, shifting geometry of motion and time. Imagine, for a moment, standing still in space, if such a thing were even possible. Earth would slide past you on its orbit, a pale blue marble racing around the sun once every year. Neptune, by contrast, would drift far more slowly, taking more than a century and a half to complete a single lap. Sometimes it is closer to us relatively speaking, and sometimes it is almost unimaginably farther away. At its closest, Neptune is still billions of kilometers distant, so far that the light leaving the sun takes hours to reach it, and yet, that closest approach is the moment when any journey outward would be least punishing. At its farthest, Neptune retreats even more deeply into the darkness, adding hundreds of millions of kilometers to an already staggering separation. You know, it's a bit like trying to meet a friend who never stops walking, while you yourself are also constantly on the move, each of you circling the same fire at the center, but at wildly different speeds. We often talk about distance in kilometers because that's what we're used to. We measure road trips, airline flights, even the circumference of our planet that way. So we say Neptune is about 4.5 billion kilometers from the sun on average, and Earth is about 150 million kilometers away. Subtract one from the other, and you might be tempted to think you have your answer. But space doesn't quite work like that. The distance between Earth and Neptune is not simply the difference between two neat numbers. Sometimes Earth and Neptune find themselves on the same side of the sun, and the gulf between them shrinks to a little over 4 billion kilometers. Other times, the sun stands between us like a vast bonfire, and Neptune is on the far side of its orbit, pushing the distance to more than 7 billion kilometers. And when you really let those numbers sink in, they begin to lose their meaning. 4 billion. 7 billion. They slide past the mind without leaving a mark. So astronomers reach for different units, gentler ones, better suited to the scale of the solar system. They speak of astronomical units, the average distance between Earth and the sun, as a kind of cosmic yardstick. In those terms, Neptune orbits at about 30 astronomical units, 30 times farther from the Sun than we are. That alone tells a story. If Earth were a single step away from the Sun, Neptune would be 30 steps out, standing alone in a cold, dim place where sunlight is little more than a bright star. But even that metaphor doesn't quite satisfy, because steps are small, intimate things. They belong to human bodies and human rooms. Neptune belongs to a different register of reality. So let's try something else. Let's imagine scaling the solar system down until Earth is the width of a grain of sand. Not the planet itself, just its orbit. A delicate ring around an invisible sun. In that model, Neptune's orbit would be hundreds of grains of sand away, scattered across a long stretch of beach. And if you were standing at Earth's position, you wouldn't even see Neptune. It would be lost beyond the curve of the shore. That's how empty space really is. Not crowded with planets and moons, but vast, overwhelmingly vast, with a few lonely islands of matter drifting through an ocean of nothing. Light gives us another way to think about this distance, perhaps a more poetic one. Light is the universe's speed limit, the fastest messenger there is. When sunlight leaves the surface of the sun, it reaches Earth in a little over 8 minutes. We feel that delay in a subtle way, though we rarely think about it. The warmth on your skin, the glow in the sky, is already 8 minutes old. Neptune, however, waits more than 4 hours for that same light. 4 hours for a sunrise that began at the sun long before. And when we send a signal, a radio whisper from Earth to a spacecraft near Neptune, we must wait those same hours for any reply. You speak, and the universe asks you to be patient. This is why Neptune feels so remote, not just physically but psychologically. It exists in a different time zone of reality. Events there are always happening hours ago from our perspective. If something dramatic were to occur near Neptune, a sudden storm or a flash of light, we would remain blissfully unaware for most of an afternoon. And that delay, that gentle but relentless lag, reminds us that distance in space is inseparable from time. To travel far is to travel into the future, step by careful step. Now, here's a way of thinking about it that I find particularly grounding, perhaps because it drags the cosmos back into the language of our everyday lives. Imagine Earth as a single human step, the length of a stride taken during a quiet walk. Just one step. In that scale, Neptune would be thousands upon thousands of football fields laid end to end, stretching away until the lines blur and the goalposts fade from view. You could walk all day and still not reach it. And you'd be walking through emptiness, not past towns or trees, but through nothing at all. No landmarks. No sense of progress, except the quiet knowledge that you are moving outward, away from the warmth and familiarity of home. And that's the thing about Neptune's position. It is not merely distant in a static way. Its orbit is slightly tilted, slightly stretched, a gentle ellipse rather than a perfect circle. Over the course of its long year, Neptune moves closer to the Sun and then farther away, tracing a slow, majestic loop that takes more than a human lifetime to complete. While it does this, Earth spins around the Sun again and again, more than 100 times, like a child running circles around a strolling adult. This mismatch in rhythm is at the heart of why reaching Neptune is so complicated. You are not chasing a stationary target. You are aiming for a moving one that will not be where it is now by the time you get there. Perhaps this is why Neptune has always carried an air of mystery. It was not discovered by simply looking and finding a bright dot in the sky. It was inferred, predicted, pulled into existence by mathematics before it was ever seen. Astronomers noticed that Uranus wobbled slightly, tugged by something unseen, and from that subtle gravitational whisper, they deduced the presence of a distant world. Neptune announced itself not through light, but through influence. And even now, its influence extends far beyond its physical size, shaping the outer solar system in ways we are still trying to understand. When you place Neptune on the true map of the solar system, stripped of artistic compression and comforting exaggeration, it forces a kind of humility upon you. The inner planets cluster close to the Sun, packed into a relatively small region of space. Even Jupiter and Saturn, vast as they are, feel almost neighborly compared to Neptune. Beyond them, the distances open up dramatically, as if the solar system takes a deep breath and stretches its limbs. Neptune sits near the edge of this stretch, a sentinel marking the transition from the familiar realm of planets to the even more diffuse regions beyond. where icy bodies drift in long, slow orbits and the sun's influence weakens. And once you start to truly feel that scale, something interesting happens. The question of how long it takes to get to Neptune stops being purely technical. It becomes philosophical. Time is no longer just something measured by clocks and calendars. It becomes a measure of commitment, of endurance, of how far we are willing to extend ourselves into the unknown. Because any journey to Neptune must contend not only with distance, but with motion. With the fact that Earth and Neptune are dancing around the sun in a complex choreography, sometimes drawing nearer, sometimes pulling apart. This brings us to a subtle but crucial realization. The distance to Neptune is not just about how far it is, but about when you choose to go. Leave at the wrong time, and you may find yourself chasing a receding world, adding years to your journey without even realizing it. Leave at the right time, and the solar system itself can seem to cooperate, shortening the path just a little, enough to matter. And that realization gently nudges us toward the next layer of the story. Because once we accept that Neptune's position is always changing, that the solar system is a dynamic place rather than a frozen diagram, we're led inevitably to the question of timing, of windows, of moments when the geometry of the planets briefly aligns in our favor, offering a narrow opportunity to slip through the cosmic machinery with less effort than we might otherwise need. And so, having placed Neptune on its true map, not as a static dot but as a moving presence in a vast, breathing system, we find ourselves naturally wondering not just where it is, but when it can be reached most wisely, how its motion and ours intertwine, and what it really means to launch a journey into a solar system that never stands still. And so, once you accept that Neptune is never truly still, that it is always gliding along its distant path while Earth loops endlessly closer to the sun, the idea of simply pointing a spacecraft outward and hoping for the best begins to feel almost naive. Because space flight, you see, is not about aiming at where something is now. It is about predicting where it will be, years from the moment you let go. And that's the thing. The solar system is a clockwork of motion, but it is not a simple one. Every planet is moving, every orbit subtly tilted and stretched, every body tugging on the others through gravity's invisible threads. To travel from Earth to Neptune is to step into that moving machinery and time your entry with extraordinary care. Picture Earth and Neptune as runners on two different tracks around the same field. Earth is sprinting on the inner lane, completing lap after lap with almost frantic energy. Neptune, by contrast, is walking the outermost track, slow, steady, unhurried, taking more than a century to complete a single circuit. If you wanted to throw a ball from Earth to Neptune, you would not aim at where Neptune is when you throw. You would aim far ahead, trusting that by the time the ball arrives, Neptune will have wandered into its path. This act of anticipation is at the heart of every interplanetary journey. And, when the distances are measured in billions of kilometers and the travel times stretch across decades, that anticipation becomes both a science and an art. Earth completes one orbit around the sun in a year. Neptune takes about 165 of those years to do the same. That difference in rhythm means their relative positions are constantly changing. Sometimes Earth catches up to Neptune from behind, finding itself roughly aligned on the same side of the sun. At other times, Earth and Neptune are separated by the full width of the solar system, with the sun blazing between them. This shifting geometry determines not only how far a spacecraft must travel, but how much energy it will need to get there. The shortest distance is not always the easiest path. The straight line, tempting as it may seem, is often the most expensive in terms of fuel. Instead, spacecraft follow long, graceful arcs known as transfer orbits. These paths are shaped by gravity, by the need to leave Earth gently rather than violently, and by the requirement to arrive at Neptune not too fast, not too slow, but just right. To do this, engineers wait for specific moments when Earth and Neptune are arranged in a favorable way. These moments are called launch windows, though the word window perhaps makes them sound more forgiving than they truly are. In reality, they are narrow cracks in time. Miss one, and you may wait years, sometimes more than a decade, for the geometry to line up again. You can think of a launch window as a fleeting conversation between planets. For a brief period, Earth says to Neptune now. Now is the moment when our motions align just enough that a spacecraft can slip away from one orbit and be gently guided toward another. Outside that moment, the same journey becomes dramatically harder. More fuel is required. Travel times increase. The mission becomes heavier, more complex, sometimes impossible with the technology at hand. And that's the thing. Space does not reward impatience. It rewards timing. The reason timing matters so much lies in gravity itself. When a spacecraft leaves Earth, it is not simply breaking free and flying straight outward. It is already moving around the Sun at tremendous speed, inherited from Earth's own orbit. To reach Neptune, the spacecraft must reshape that solar orbit, stretching it outward until it intersects Neptune's path at precisely the right moment. This reshaping takes energy, and energy in spaceflight usually means fuel. Fuel is heavy. Heavy things are hard to launch. So mission designers become masters of compromise, looking for ways to let gravity do as much of the work as possible. Earth's position at launch determines the initial direction and shape of the spacecraft's trajectory. Neptune's position years later determines where that trajectory must end. The launch window exists when these two requirements can be satisfied at once. If Earth launches too early, the spacecraft arrives at Neptune's orbit long before Neptune itself. Too late, and Neptune has already passed, leaving the spacecraft to chase it from behind, a futile and costly pursuit. The window opens, lingers briefly, and then closes, indifferent to our readiness or our desires. There is something quietly humbling about this. We like to think of ourselves as explorers, as masters of technology, capable of bending nature to our will. But in interplanetary travel, we are more like surfers waiting for the right wave. We cannot create the wave. We can only study the ocean of motion and hope to be in the right place at the right time. When the wave comes, we must be ready, because it will not wait. Neptune's slow orbit adds another layer of complexity. Because it moves so slowly, favorable alignments with Earth are relatively rare. The launch windows that allow for efficient travel to Neptune do not come every year, or even every few years. They may be separated by decades, depending on the exact trajectory you wish to fly and whether you plan to involve other planets along the way. And this means that the decision to go to Neptune is never just a scientific one. It is a generational one. The engineers who design the mission may never see its results. The scientists who propose the questions may retire long before the data arrives. Time stretches not just in space, but in human lives. Consider what happens if you ignore launch windows altogether. Suppose you insist on launching whenever you like, without regard for planetary alignment. The spacecraft can still go, of course. Physics does not forbid it. But the cost rises sharply. You must carry far more fuel to force your way onto the desired path. The spacecraft becomes heavier, the rocket larger, the mission more expensive. In some cases, the required energy exceeds what our launch vehicles can provide. The destination does not change, but it recedes beyond our practical reach. Timing, then, is not a convenience. It is a gatekeeper. This dance of orbits also means that the travel time to Neptune is not a fixed number. It depends on when you leave. One launch window might offer a journey of 12 years. Another might stretch that to 15 or even 20. These differences arise from subtle changes in geometry, from the angle at which you depart Earth and the speed you carry into interplanetary space. Small differences at the beginning compound over billions of kilometers, magnifying into years by the time you arrive. And when you start to see it this way, you realize that the solar system is not laid out for our convenience. It is indifferent to our schedules, our funding cycles, our political timelines. The planets move as they always have, and will continue to do so long after we are gone. To explore them, we must adapt ourselves to their rhythms, not the other way around. There is also the question of relative inclination. Earth's orbit and Neptune's orbit are not perfectly aligned. Neptune's path is tilted slightly relative to the plane in which Earth moves. That tilt may seem small, but over vast distances it matters. Launching at the wrong time can mean that a spacecraft arrives at Neptune's distance, but above or below the plane of Neptune's orbit, missing it entirely. Correcting such an error requires additional energy, further tightening the constraints on when a mission can sensibly begin. So mission planners look for windows when Earth is not only in the right place around the Sun, but also when the plane of the transfer orbit lines up favorably with Neptune's own path. These considerations stack upon one another, narrowing the window further. What remains is a brief interval, sometimes measured in weeks, during which a launch makes sense. Outside that interval, the door quietly closes. It is worth pausing here, I think, to reflect on how counterintuitive this all is. From our everyday perspective, waiting seems passive. Doing nothing feels like a failure of action. But in space exploration, waiting is often the most active choice you can make. Waiting for the planets to align is a form of respect. It is an acknowledgement that the universe operates on timescales and patterns larger than our own. And when we wait well, when we choose our moment carefully, we are rewarded with journeys that would otherwise be impossible. Neptune's great distance magnifies the importance of these choices. A mistake made at launch cannot be easily undone. There are no pit stops in deep space, no convenient places to refuel or turn around. Once the spacecraft is on its way, it is committed, carrying with it all the assumptions and calculations made years earlier. The launch window, fleeting though it is, imprints itself on the entire mission, shaping its duration, its cost, and its ultimate success. As we think about these windows, it becomes clear that the journey to Neptune is not a single act, but a sequence of carefully timed events. The launch itself is only the beginning. The initial trajectory sets the stage for everything that follows. And here, quietly waiting in the background, is another idea, one that begins to shimmer into view once timing enters the conversation. Because if we are already relying on the motion of the planets to help us, if we are already shaping our path to align with their orbits, then it is natural to ask whether we might do more than simply aim for Neptune directly. Perhaps you might wonder, there are ways to borrow energy from other worlds along the way. Perhaps the solar system, in all its motion, offers not just obstacles, but opportunities. Ways to gain speed without carrying extra fuel. Ways to turn timing itself into a source of propulsion. And as that thought takes hold, as the idea of using the planets not just as destinations, but as partners begins to form, we find ourselves on the threshold of another layer of the journey, one where speed and history intertwine, and where a single spacecraft long ago showed us just how powerful careful timing can truly be. And so, with the idea of timing still gently echoing in the background, with the realization that the planets themselves can either open doors or quietly close them, we arrive at a remarkable moment in human history, a moment when all of these abstract ideas were tested not in theory, not in simulation, but in the cold, unyielding reality of space itself. Because there was, you see, one spacecraft that actually made the journey, one silent traveler that left Earth and, many years later, passed by Neptune, offering us a fleeting glance at a world we had never seen up close before. And that's the thing. When we ask how long it really takes to reach Neptune, we are not speaking entirely in hypotheticals. We have, tucked away in our collective memory, a real answer, written not in equations, but in the long arc of a single mission. Voyager 2 did not begin its life with Neptune as its primary goal. In fact, when it lifted away from Earth, carried by a pillar of fire and hope, its mission was broader, almost audacious in its ambition. It was part of a grand alignment, a rare celestial arrangement in which the giant planets lined up in such a way that a spacecraft could visit them one after another, using each world's gravity as a stepping stone to the next. This alignment occurs only once every many lifetimes, and the people who recognized it knew that if they did not act, the opportunity would slip away, perhaps not to return for centuries. And, they chose to act. Voyager 2 was launched in the late 1970s, at a time when computers filled rooms and had less processing power than the devices we now carry in our pockets. Its memory was tiny. Its instruments were modest by modern standards, and yet it carried something far more important than raw computational strength. It carried foresight. The mission designers understood the language of orbits and timing well enough to write a trajectory that would carry this small machine across the solar system, planet by planet, world by world, without refueling, without course corrections of any great magnitude, relying instead on gravity itself to do most of the work. The journey to Neptune was not direct. It was a long, looping pilgrimage through the outer solar system. Voyager 2 first encountered Jupiter, then Saturn, then Uranus, each flyby carefully choreographed. At each planet, gravity reached out and reshaped the spacecraft's path, stealing a tiny bit of orbital energy from the massive world and gifting it to the spacecraft instead. This exchange was subtle, elegant, and incredibly powerful. By the time Voyager 2 set its sights on Neptune, it was moving faster than any human-made object had ever traveled before, not because it carried vast amounts of fuel, but because it had learned to dance with the planets. From launch to Neptune, the journey took about 12 years. 12 years of continuous flight through deep space. 12 years during which Earth itself changed. Governments rose and fell. Technologies evolved. Children were born who would grow into adults before the mission reached its climax. And all the while, Voyager 2 kept going, faithfully transmitting whispers of data back across billions of kilometers, each signal taking hours to reach us. There is something profoundly moving about that, I think. A machine built by human hands, traveling for more than a decade, guided by mathematics and patience, carrying with it the curiosity of an entire species. When Voyager 2 finally approached Neptune, it did not slow down. There was no braking burn, no attempt to settle into orbit. It flew past in a brief, precious window of time, gathering as much information as it could before continuing onward into the darkness. For a few short hours, Neptune was no longer an abstract concept or a faint point of light. It was a real place, with storms and clouds and rings and moons, revealed in astonishing detail for the first time. The great dark spot loomed in its atmosphere, a reminder that even in the cold outskirts of the solar system, dynamic and violent processes were at work. The flyby taught us many things, but perhaps the most important lesson was not about Neptune itself. It was about what is possible when we respect the structure of the solar system. Voyager 2 did not reach Neptune quickly by brute force. It reached Neptune efficiently by intelligence. Its 12-year journey remains the fastest we have ever made to that distant world, not because we cannot build faster rockets today, but because that particular alignment of planets, that precise sequence of gravitational assists, has not presented itself again in quite the same way. This is a subtle but crucial point. When people hear that Voyager 2 took 12 years to reach Neptune, they sometimes assume that 12 years is the baseline. That with enough funding or political will, we could simply do it again on demand. But the reality is more nuanced. Voyager 2's trajectory was a once-in-a-generation gift from the cosmos. It relied on Jupiter, Saturn, and Uranus all being in the right places at the right times, allowing the spacecraft to hop from one to the next like stones across a river. Without that alignment, the same journey would have taken much longer, or required far more energy than was available. In that sense, Voyager 2 was not just a spacecraft, it was a message from the universe, telling us that timing matters as much as technology, that patience and planning can sometimes achieve what raw power cannot. And when you sit with that idea for a moment, it starts to feel like a broader truth, one that extends beyond space exploration and into the fabric of human endeavor itself. There were limitations, of course. Voyager 2 carried instruments designed for flybys, not long-term study. It could not linger. It could not return. Once it passed Neptune, it was committed to a new chapter of its journey, one that would take it beyond the planets entirely, into interstellar space. Neptune, for all its beauty and mystery, was a brief encounter, a passing conversation rather than a sustained relationship. And yet, that fleeting visit reshaped our understanding of the outer solar system. We learned that Neptune radiates more heat than it receives from the sun, hinting at internal processes still not fully understood. We discovered a complex ring system and a retinue of moons, including Triton, with its strange retrograde orbit and geysers of nitrogen ice erupting from its surface. These findings challenged our assumptions and opened new questions, reminding us that the farther we go, the more the universe resists simple explanations. But in the context of our larger question, Voyager 2's greatest gift was perspective. It showed us that reaching Neptune is not impossible, but it is not trivial either. 12 years may sound short on cosmic timescales, but on human timescales it is enormous. It requires sustained commitment across decades, from initial concept to final data analysis. It requires institutions that can think beyond election cycles and funding rounds. It requires a willingness to plant seeds whose fruit you may never personally harvest. And that's the thing. Voyager 2 was designed and launched by people who knew they might not be there to see its final triumph. They worked anyway. They trusted the process. They trusted that knowledge itself was worth the wait. In doing so, they set a standard not just for space missions, but for long-term thinking of any kind. As the spacecraft sped past Neptune and continued onward, it carried with it a kind of quiet proof. Proof that with the right alignment of minds and planets, with careful attention to timing and motion, we can bridge distances that once seemed insurmountable. But it also left us with a question that lingers to this day. If 12 years was the best we could do under nearly perfect circumstances, what does that say about journeys made under less ideal conditions? Because Voyager 2 was fast, but it was fast in a very specific way. Its speed was the result of borrowed energy, carefully accumulated over multiple encounters. Remove any one of those encounters, shift the timing slightly, and the outcome changes dramatically. The journey grows longer. The demands grow heavier. And so, as we look back on this singular mission, we are naturally led forward to the next layer of understanding. If timing and gravity can make such a difference, if a carefully chosen path can shave years off a journey measured in decades, then speed itself becomes the central character in our story. Not speed as we experience it on highways or in aircraft cabins, but speed in its raw, unforgiving, cosmic form. How fast can we really go? What limits that speed? And how does that speed translate into time when the destination is billions of kilometers away and moving all the while? With Voyager 2 as our reference point, as our benchmark etched into history, our attention begins to shift from where and when to how fast, and in that shift, the true scale of the challenge ahead starts to come into focus. And so, with Voyager 2 still fading into the background like a distant memory, its triumph etched quietly into the long ledger of human exploration, our attention turns naturally to the invisible force that shaped every moment of that journey: speed. Not the kind we feel when a car accelerates or when an aircraft lifts from the runway, but speed stripped of comfort and intuition, speed measured against distances so large that our instincts simply fall away. Because when you're traveling to Neptune, speed is not a luxury. It is everything. You see, distance by itself does not decide how long a journey takes. Distance is silent. It merely waits. It is speed that gives distance a voice, that turns emptiness into years, into decades, into lifetimes. And that's the thing. When people ask how long it takes to reach Neptune, they are really asking how fast we can move through the solar system, and how fast we can afford to move without tearing ourselves or our machines apart. At its heart, the relationship is deceptively simple. Time equals distance divided by speed. It is one of the first equations we learn, taught to children with toy cars and stopwatches. But in space, that innocent formula becomes unforgiving. The distance to Neptune is so vast that even small changes in speed ripple outward into enormous differences in travel time. Increase your speed slightly, and you shave off years. Slow down just a little, and the journey stretches beyond the span of a human career. Let's ground this in something familiar. Imagine driving a car at highway speed, perhaps 100 kilometers per hour. At that pace, crossing a continent feels manageable. But aim that car toward Neptune, and the numbers become absurd. At car speed, the journey would take tens of thousands of years. Civilizations would rise and fall while you crawled through the void, your destination forever out of reach. And that realization alone tells us something important. Everyday speeds, the speeds our bodies are built for, simply do not belong on the cosmic stage. So we step up. We imagine a jet aircraft, slicing through the sky at nearly 1,000 kilometers per hour. That feels fast to us. It compresses the world. Oceans shrink to hours. But even at that speed, Neptune remains stubbornly distant. The journey would still take thousands of years. Faster than the car, yes, but still hopelessly slow when measured against planetary scales. Then we turn to rockets, to the machines designed specifically to escape Earth's grip. Chemical rockets can reach speeds of tens of thousands of kilometers per hour once they are free of the atmosphere. Now we are beginning to speak the language of space. At these speeds, the inner solar system becomes accessible. Mars is weeks away, Jupiter is months. But Neptune still waits, patient and unmoved. Even at these impressive velocities, the journey stretches into decades. Voyager 2, at its peak, was traveling at around 50,000 kilometers per hour relative to the Sun. That is a number so large it barely fits into the mind. And yet, even at that speed, it took 12 years to reach Neptune under ideal conditions. 12 years of relentless motion, every second carrying it forward faster than any vehicle on Earth, and still the distance demanded its due. This is where our intuition begins to fail us. We are used to thinking of speed as something we can simply add, press harder on the accelerator, build a bigger engine, burn more fuel. But in space, speed is expensive. To go faster, you must carry more propellant. To carry more propellant, you must launch more mass. To launch more mass, you need an even bigger rocket. This feedback loop is merciless, governed by the rocket equation, a law of physics that offers no exceptions and no sympathy. The rocket equation tells us that each increment of additional speed requires exponentially more fuel. This is why rockets shed stages as they climb skyward, discarding empty tanks like husks. It is why most of a rocket's mass at launch is fuel, not payload. And when you are aiming for Neptune, the tyranny of this equation becomes absolute. You cannot simply brute force your way there by piling on more fuel. At some point, the numbers stop making sense. This is why Voyager 2's speed was not achieved through raw propulsion alone. It was achieved through strategy, through patience, through letting gravity itself do the heavy lifting. But even so, there are limits. Gravity assists can only add so much speed. Chemical rockets can only provide so much initial push. And that brings us face to face with a sobering truth. With current propulsion methods, there is a ceiling to how fast we can realistically go. There are other kinds of engines, of course. Ion engines whisper rather than roar, expelling particles at incredible speeds but with tiny thrust. Over time, that gentle push can build up to impressive velocities. But ion engines accelerate slowly. They are not well suited to rapid departures from Earth, and while they can outperform chemical rockets in efficiency, they still operate within the same cosmic constraints. Speed accumulates, but the distances remain vast. And so, when we speak of speed in the context of reaching Neptune, we are really speaking of trade-offs. Do you want to arrive sooner, or do you want to carry more instruments? Do you want flexibility, or do you want efficiency? Every decision reshapes the trajectory, the timeline, the very character of the mission. There is also the matter of relative speed. Speed with respect to what? A spacecraft leaving Earth already has Earth's orbital velocity around the Sun, about 100,000 kilometers per hour. This inherited motion is a gift. It means we are not starting from rest, but it also means that changing direction is costly. To slow down, to speed up, to tilt the orbit, all of these maneuvers require energy. In space, motion is precious. You guard it carefully. This is why straight-line travel is almost never used. Flying directly toward Neptune would require canceling much of Earth's orbital speed and then rebuilding it in a new direction. The energy cost would be enormous. Instead, spacecraft follow curved paths that respect the flow of the solar system. Speed is adjusted gradually, nudged rather than forced. And this brings us to an uncomfortable but illuminating comparison. Light. Light crosses the distance from the Sun to Neptune in a little over 4 hours. That is the benchmark set by the universe itself. And yet, even our fastest spacecraft crawl along at a tiny fraction of that speed. Voyager 2 was moving at about 1/50,000th the speed of light. To reach 1% of light speed would require propulsion systems far beyond anything we currently possess. Systems that challenge our understanding of materials, energy generation, and control. This gap between what is physically possible in principle and what is technologically achievable in practice defines the frontier of space travel. We know that faster journeys are conceivable. The equations allow it. But knowing something is possible is not the same as being able to do it. Between those two lies a vast gulf of engineering, economics, and patience. Speed also has consequences. Arriving at Neptune too fast is as much a problem as arriving too slow. If a spacecraft is moving too quickly, it cannot easily slow down to enter orbit. It will scream past, offering only a brief glimpse before vanishing into the darkness. This is what happened with Voyager 2. Its speed made orbit insertion impossible with the fuel it carried. The choice was deliberate. Better a fast flyby than no encounter at all. This trade-off becomes especially important when we imagine future missions. A slower approach allows for richer science, more time, more control. But it also means a longer journey, more exposure to radiation, more wear on systems, more years of waiting. Speed, then, is not a single variable to maximize. It is a knob to be tuned carefully, balanced against every other constraint. There is a philosophical layer to this as well, one that is easy to miss amid the equations and engineering diagrams. Speed shapes our relationship with time. A 12-year journey demands a different mindset than a 3-year journey. It asks for long-term thinking, for continuity across generations of scientists and engineers. It asks institutions to remain stable, goals to remain clear, curiosity to remain alive even as people come and go. And that's the thing. When we talk about speed, we are really talking about how we choose to engage with the future. Do we rush, accepting limitations in exchange for immediacy? Or do we move more slowly, patiently, building missions that unfold over decades? Neptune, distant and unhurried, seems to invite the latter approach. It does not reward haste, it rewards persistence. As we stand here, conceptually speaking, having traced the limits of speed imposed by our current technologies, we begin to sense the shape of the next question forming. If speed is so crucial, if it governs everything from travel time to mission design, then perhaps the most important question is not how fast we can go on our own, but how fast we can go with help. Because the solar system is not empty. It is filled with massive worlds moving at incredible speeds, each one carrying a reservoir of orbital energy. If we could find ways to tap into that energy, to borrow it briefly without paying an impossible price in fuel, then speed itself might take on a new character. It might become something we negotiate rather than something we purchase outright. And as that idea begins to crystallize, as the notion of using planets as allies rather than obstacles comes into focus, we are gently drawn toward the elegant trick that made Voyager 2's record-breaking journey possible in the first place. The quiet, almost magical exchange known as gravity assist, where speed is not created, but shared. And so we arrive at the quiet trick that changes everything. The moment where speed is no longer something you must buy entirely with fuel, mass, and sacrifice, but something you can borrow, briefly, elegantly from the motion of the planets themselves. This is where gravity assist enters the story, not as a loophole in physics, but as a deep cooperation with it. And once you truly understand what is happening here, you begin to see the solar system not as a set of obstacles scattered across space, but as a moving network of opportunities, each planet carrying within it a vast reserve of energy, patiently waiting to be tapped. At first glance, the idea sounds almost like magic. A spacecraft approaches a planet, swings around it, and leaves moving faster than before, all without firing its engines in any significant way. No fuel burned, no obvious push applied. Just motion gained seemingly for free. But of course, nothing in the universe is free. Energy is conserved. What the spacecraft gains, the planet must give up, though in such a tiny amount that the planet never notices. Jupiter does not slow in any meaningful sense. Saturn does not drift out of place. Their masses are simply too large. And that's the thing. When you place something small next to something unimaginably massive, the rules feel almost unfair. To understand gravity assist, it helps to let go of the image of a spacecraft being slung like a stone from a sling. That metaphor is common, but it hides what really matters. The true exchange happens not in the spacecraft's frame of reference, but in the sun's. As a planet moves around the sun, it carries orbital energy with it. When a spacecraft approaches from behind, matching its path just right, it can steal a tiny fraction of that energy, leaving the encounter moving faster relative to the sun than it was before. From the spacecraft's perspective, the planet seems to pull it forward. From the planet's perspective, nothing of consequence has happened. From the sun's perspective, energy has been redistributed. This redistribution is subtle and beautiful. It requires precision. Approach the planet too closely, and you risk destruction. Miss it by too much, and the effect is negligible. The angle matters. The timing matters. The speed at arrival matters. Everything matters. Gravity assist is not a brute force maneuver. It is choreography. Jupiter is the great benefactor in this dance. Massive beyond comprehension, moving swiftly around the sun, it is the solar system's most generous energy reservoir. A spacecraft that passes behind Jupiter can gain an enormous boost in speed, far more than it could reasonably generate on its own. This is why Jupiter appears again and again in the trajectories of missions headed to the outer solar system. It is the gatekeeper. Saturn, while less massive, still offers substantial assistance, and Uranus and Neptune themselves can shape trajectories in more subtle ways. For a journey to Neptune, gravity assist is not optional if you want efficiency. Without it, the fuel requirements become extreme, and the travel time stretches uncomfortably long. With it, suddenly, Neptune feels just a little closer, still far, still demanding, but no longer absurdly so. Voyager 2 was the most famous beneficiary of this method. But it was not alone. Many missions have used gravity assists to reshape their paths, to save fuel, to reach destinations that would otherwise be out of reach. What made Voyager 2 special was the sequence. Jupiter handed it off to Saturn. Saturn passed it onward to Uranus. Uranus nudged it toward Neptune. Each encounter carefully planned years in advance, each dependent on the precise positions of worlds millions of kilometers across. This is where the idea of planetary alignment becomes more than an abstract curiosity. For gravity assist to work in sequence, the planets must be arranged in just the right way. Not simply lined up in a straight line, but positioned so that a spacecraft leaving one encounter naturally intersects the orbit of the next planet at the right time and angle. These alignments are rare. They occur over timescales that dwarf human planning horizons. And when they happen, they offer a fleeting chance to do something extraordinary. For Neptune, the most powerful gravity assist scenarios involve Jupiter and Saturn. Jupiter provides the initial, dramatic acceleration, flinging the spacecraft outward with newfound speed. Saturn can refine the trajectory, adjusting inclination and direction, shaping the path so that it intersects Neptune's orbit years later. Each planet acts like a turning point in a long sentence written across space, each comma placed with care. But gravity assist has limits. It cannot give you infinite speed. The maximum boost depends on the planet's mass and orbital velocity, and on how close and how precisely you pass. You cannot extract more energy than the planet can spare, and you cannot bend physics to your will. There is also a cost in flexibility. Once you commit to a gravity assist trajectory, your options narrow. Miss a flyby window, and the entire chain can unravel. The elegance of the method comes with fragility. There is also risk. Passing close to a giant planet exposes a spacecraft to intense radiation, especially around Jupiter, whose radiation belts are among the most hostile environments in the solar system. Instruments must be shielded. Electronics hardened. Every close approach is a gamble, trading speed for danger. And that trade-off is accepted because the alternative is often worse. Slower travel means longer exposure to cosmic radiation, more time for systems to fail, more years of uncertainty. Gravity assist also locks you into a schedule set by the planets, not by mission planners. You must arrive at Jupiter when Jupiter is there, moving at the right speed and angle. You cannot ask it to wait. This reinforces a theme that keeps returning in this story. The universe does not adapt to us, we adapt to it. For Neptune, the window for using Jupiter and Saturn effectively is not always open. Decades can pass between favorable opportunities. During those times, missions must either accept much longer travel times or explore alternative propulsion methods. This is why Voyager 2 remains unique. It rode a wave of alignment that has not repeated in quite the same way since. There is something deeply poetic about this. The fastest journey humanity has ever made to Neptune depended not on brute technological supremacy, but on listening, on understanding the rhythms of the solar system well enough to slip between them. It was less like conquering a mountain and more like navigating a river, reading currents, anticipating bends, letting the flow carry you farther than your own strength ever could. Yet even with gravity assist, the journey remains long. Years pass. Data trickles back slowly. The spacecraft becomes a kind of time capsule, built with technology that will be obsolete long before it arrives. Engineers must think not just about where the spacecraft will go, but about what the world on Earth will be like when it gets there. Will the antennas still be listening? Will the institutions still exist? Will anyone remember why the mission was launched in the first place? Gravity assist, then, is not just a technical trick. It is a philosophical stance. It says that progress does not always come from pushing harder. Sometimes it comes from aligning better, from recognizing that the environment you move through has structure and energy, and that if you respect that structure, you can go farther than you ever could alone. But this method also highlights a hard truth. Even with the help of the largest planets, even with perfect timing and flawless execution, the speeds we can achieve are still modest by cosmic standards. Neptune remains a decade-long journey at best. Gravity assist helps, but it does not erase the vastness. It only makes it manageable. And so, as we absorb the power and the limits of gravity assist, another comparison begins to emerge naturally. If gravity can lend us speed, what about our engines themselves? What are they really capable of? How do the roaring chemical rockets that lift us from Earth compare to the quiet, persistent push of ion engines that operate over years. If gravity assist is about borrowing energy from the environment, then propulsion is about how we generate and spend our own. The contrast between these approaches is stark. One is explosive, immediate, dramatic. The other is patient, efficient, almost meditative. And as we continue to peel back the layers of what it would truly take to reach Neptune, the conversation inevitably shifts from borrowed speed to earned speed, from gravity's gifts to the tools we build ourselves. It is there, in that comparison, that the next chapter quietly begins, where the nature of propulsion itself comes under scrutiny, and where the question of how we push against the universe becomes just as important as when we choose to go. And so, having learned how to borrow speed from the giants of the solar system, having seen how gravity itself can become a silent partner in our journeys, we are left with a quieter, more intimate question. When gravity is no longer enough, when alignments do not favor us, when patience alone cannot shorten the years, what do we rely on then? We rely on our engines, on the tools we build to push ourselves forward against the vast inertia of space. And here, the contrast could not be more striking, because the two dominant forms of propulsion we use today, chemical engines and ion engines, could hardly be more different in character, in rhythm, and in what they ask of us as explorers. Chemical rockets are the thunder of spaceflight. They are violent, brief, and overwhelmingly powerful. When one ignites, it does so with a ferocity that shakes the ground and rattles the bones of those nearby. Enormous quantities of fuel are burned in a matter of minutes, producing thrust strong enough to lift thousands of tons off the surface of Earth and hurl them skyward. This kind of power is intoxicating. It feels decisive, it feels like progress made visible. And, for escaping Earth's gravity, well, there is still nothing that matches it. But that's the thing. Chemical rockets are sprinters. They are built for the opening act, not the long journey. Almost all of their fuel is expended in the first few minutes of flight. By the time a spacecraft is coasting in orbit, the roaring engines are long silent, their work done. What remains is momentum, inherited speed, and a vehicle that must now make do with what it has. For journeys to the outer solar system, chemical propulsion sets the stage. It provides the initial shove that sends a spacecraft on its way. It can perform course corrections, adjust trajectories, and in some cases slow a spacecraft down for orbit insertion. But every maneuver consumes fuel, and fuel is finite. Once it is gone, the spacecraft becomes a drifting object, bound entirely by gravity and inertia. Ion engines, by contrast, are almost humble in their presence. If chemical rockets shout, ion engines whisper. They produce thrust so gentle that you could rest a coin on your hand and not feel it move. And yet, they operate continuously, day after day, month after month, year after year. Instead of burning fuel in an explosive reaction, ion engines use electricity to accelerate charged particles to extraordinary speeds, ejecting them in a steady stream. The thrust is tiny, but the efficiency is remarkable. Efficiency is the key word here. Ion engines extract far more momentum from a given amount of propellant than chemical engines ever could. They sip fuel rather than guzzle it. This means that over long durations, they can achieve changes in speed that rival or even exceed those produced by chemical propulsion, all while carrying far less propellant. The trade-off is time. Ion engines take patience. They demand a willingness to think not in minutes or hours, but in months and years. For a journey to Neptune, this difference in character matters deeply. Chemical propulsion can get you moving quickly, but it cannot sustain acceleration over the long haul. Ion propulsion can accelerate almost indefinitely, but only if you are willing to wait. It is the difference between a powerful leap and a long, steady climb. Imagine two travelers setting out across a vast desert. One has a powerful burst of speed at the beginning, sprinting far ahead before collapsing into a walk. The other moves slowly but never stops, taking one step after another, day and night. At first, the sprinter seems to be winning. But over time, the steady traveler begins to close the gap. In the context of spaceflight, ion engines are that steady traveler. There is another subtlety here, one that often goes unnoticed. Chemical engines are limited not just by fuel, but by heat and pressure. The materials must withstand extreme conditions for short periods. Ion engines operate at much lower stresses. They can be turned on and left running for years, their quiet glow a testament to endurance rather than brute force. This makes them particularly attractive for deep space missions, where reliability over long timescales is essential. However, ion engines come with their own constraints. They require electricity, often generated by solar panels. As you move farther from the sun, sunlight grows weaker. At Neptune's distance, the sun is a bright star, but not much more. Solar power becomes impractical. To run ion engines that far out, you need alternative power sources, typically nuclear. This introduces complexity, cost, and political challenges. It is not a simple substitution. Chemical propulsion, in contrast, does not care how far you are from the sun. It carries its energy with it, locked in chemical bonds, ready to be released on demand. This independence is powerful. It allows missions to operate in the darkest reaches of the solar system without relying on external energy sources. But again, the price is inefficiency. So which is better for reaching Neptune? The answer, frustratingly, is that neither is perfect on its own. Chemical propulsion excels at the beginning and sometimes at the end. Ion propulsion excels in the middle, during the long, quiet cruise through deep space. This is why many mission concepts blend the two, using chemical rockets to escape Earth and set the initial trajectory, and ion engines to reshape that trajectory gradually over time. In such hybrid missions, the spacecraft might leave Earth on a chemical rocket, gain initial speed, perhaps even take advantage of gravity assist, and then engage its ion engines for years, slowly building additional velocity. This approach can reduce travel time without requiring impossible amounts of fuel. But it also extends the mission duration, increases operational complexity, and demands systems that can function flawlessly for decades. And here we encounter another important limitation. Time itself becomes a resource. The longer a mission takes, the more opportunities there are for failure. Electronics age, components degrade, software becomes outdated, teams change, institutional memory fades. A mission that relies on ion propulsion for many years must be designed not just for performance, but for longevity. There is also the question of control. Chemical burns are decisive. You ignite the engine. You change your velocity significantly in a short time. Ion propulsion is subtle. Course corrections happen slowly. This requires precise navigation and constant monitoring. It is a different style of flying, more like steering a sailboat than driving a car. For Neptune, this style may be appropriate. The planet is not going anywhere. Its orbit is slow and predictable. A gradual approach allows for fine-tuning, for adapting to small uncertainties along the way. But it also demands a mindset comfortable with delay, with the idea that progress can be almost invisible on human timescales. Perhaps this is why chemical propulsion still dominates our imagination. It aligns with our instincts. Fire equals motion, explosion equals power. Ion propulsion, by contrast, feels almost counterintuitive. How can something so gentle accomplish something so vast? And yet, when you step back and look at the numbers, when you integrate tiny thrust over millions of seconds, the answer becomes clear. Persistence can rival strength. There is a deeper lesson here, one that echoes through this entire exploration of Neptune. The universe is not impressed by force alone. It responds to consistency, to alignment, to respect for underlying laws. Chemical rockets embody our desire to break free, to escape quickly, to overcome gravity in a dramatic gesture. Ion engines embody our willingness to adapt, to work within constraints, to let time itself become part of the engine. Neither approach is wrong. They are simply different expressions of how we choose to move through the cosmos. And for a destination as distant as Neptune, it is likely that both will play a role, intertwined with gravity assists and careful timing, forming a tapestry of techniques rather than a single solution. As we weigh these options, as we compare the roar of chemical thrust to the whisper of ion acceleration, another realization quietly emerges. All of this discussion assumes machines, uncrewed spacecraft, silent travelers that do not breathe, do not age, do not grow weary. We have spoken of fuel and power and efficiency, as if time were merely an engineering parameter. But the moment we imagine humans making this journey, everything changes. Speed is no longer just about efficiency. Duration is no longer just a number. The long, patient timelines that ion engines invite, the decade-long cruises enabled by gravity assist, begin to clash with the fragile biology of the human body. Radiation, isolation, muscle loss, psychology. These forces do not care how elegant our propulsion systems are. They impose their own limits, limits that cannot be solved with better equations alone. And so, as the contrast between chemical and ion propulsion settles into place, As we begin to appreciate what each can and cannot offer, our thoughts are inevitably drawn toward the next great constraint in the story. Not engines, not gravity, but ourselves. The living, breathing beings who dream of going farther than any of these machines were ever meant to carry us. And so the conversation shifts, almost reluctantly, away from engines and equations and elegant trajectories, and toward something far more fragile, the human body. Because all the strategies we have explored so far, gravity assists, ion propulsion, chemical thrust, they all quietly assume that the traveler does not age, does not weaken, does not feel loneliness or fear. They assume a machine. And that assumption works beautifully right up until the moment we imagine a person on board. You see, space is not just empty. It is hostile in ways that are subtle, persistent, and deeply indifferent to biology. On Earth, we are wrapped in layers of protection we rarely think about. A thick atmosphere that absorbs radiation, a magnetic field that deflects charged particles, gravity that pulls on our bones and muscles every second of our lives, shaping us from the moment we are born. Remove those protections and the body begins to change, quietly at first, then unmistakably. One of the earliest challenges is radiation. Beyond Earth's protective shield, cosmic rays and energetic particles from the sun pass freely through space. They are invisible, silent, and relentless. Over short missions, the risk is manageable. Over years, it becomes profound. Radiation damages DNA. It increases the risk of cancer. It affects the nervous system in ways we are only beginning to understand. And that's the thing. A journey to Neptune is not measured in weeks or months. It is measured in decades, especially if we imagine a crewed mission that must slow down, conserve resources, and perhaps even return. Shielding can help, but shielding is heavy. Every extra layer of protection adds mass, which demands more fuel, which extends the journey, which increases radiation exposure even further. It is a cruel loop. Engineers can optimize, but they cannot escape the trade-off entirely. Radiation becomes a ticking clock, counting not seconds, but cellular damage. Then there is microgravity. Our bodies evolved under a constant downward pull. Bones thicken and strengthen in response to load. Muscles grow when they are used against resistance. Remove that load, and the body adapts just as efficiently, but in the opposite direction. Bones lose density, muscles atrophy. The heart changes shape. Astronauts returning from months aboard space stations must relearn how to stand, how to walk, how to trust their own strength. Exercise can slow this process, but it cannot fully stop it. On a journey lasting many years, even the most rigorous routines may not be enough. The body is not designed for permanent weightlessness. And this is not just an inconvenience. Reduced bone density increases the risk of fractures. Muscle loss reduces strength and endurance. These changes could compromise a crew's ability to perform tasks, respond to emergencies, or even survive landing on another world. Psychology, too, becomes a formidable challenge. Humans are social creatures. We are shaped by variety, by novelty, by contact with others. A journey to Neptune would confine a small group of people to a limited space for years, possibly decades, with no possibility of rescue, no fresh faces, no true privacy. Even the view outside the window would change only slowly, the stars shifting almost imperceptibly over time. Isolation of this magnitude is not simply boredom. It can erode mental health. Depression, anxiety, interpersonal conflict, cognitive decline all become risks. On Earth, isolation can be relieved. In deep space, it cannot. Every disagreement must be resolved internally. Every emotional crisis must be endured without external support. The psychological load becomes as real as the physical one. There is also the question of time perception. On Earth, time is marked by cycles. Day and night, seasons, social rhythms. In deep space, those markers blur. Artificial lighting can simulate a day-night cycle, but it is an imitation. Over years, the lack of natural temporal anchors can distort perception, making time feel either endless or vanishingly short. Both extremes are dangerous for morale and mental stability. Then there is the simplest, most human problem of all: aging. A crew that leaves Earth in their 30s could arrive at Neptune in their 50s or 60s, depending on the trajectory and propulsion used. Their bodies would not be the same. Their reaction times would slow. Their resilience would change. Planning a mission that spans such a large fraction of a human lifespan raises questions that are as ethical as they are technical. Who volunteers for such a journey? Who bears the risk? Who takes responsibility if something goes wrong decades after launch? These are not questions with easy answers. They force us to confront the limits of exploration driven by human presence. Life support adds another layer of complexity. Food, water, oxygen, waste recycling, all must function flawlessly for years. Redundancy is essential, but redundancy adds mass and complexity. Systems must be repairable by the crew using limited tools and materials. Every component becomes critical. There is no resupply, no emergency shipment. The ship must be a closed world, sustaining life indefinitely in an environment fundamentally hostile to it. This is why, when we look honestly at the problem, sending humans to Neptune with current technology feels less like an engineering challenge and more like a biological one. Our machines might endure. Our bodies might not, and that's the thing. The constraints here are not imposed by physics alone. They are imposed by evolution, by the fact that we are the product of a planet that nurtured us gently and continuously. Robotic missions do not share these vulnerabilities. They do not fear radiation. They do not lose bone density. They do not suffer from isolation or homesickness. They can wait. They can drift silently for decades, powered by small amounts of energy, performing their tasks without complaint. This is why, for now, Neptune remains a destination for machines rather than people. And yet, there is a quiet sadness in that realization. Robots can gather data, but they cannot wonder. They cannot feel the weight of standing beneath a distant sun. They cannot look at Neptune's blue clouds and feel awe. Human presence adds something intangible to exploration, something that numbers and images alone cannot replace. This tension, between what we can do and what we wish to do, runs through every discussion of deep space travel. Neptune sits at the far edge of what feels emotionally reachable, close enough to dream about, far enough to resist us. It forces us to confront not just the limits of our technology, but the limits of our bodies and minds. Perhaps this is why so many proposals for human journeys to the outer solar system include ideas that feel almost like science fiction. Artificial gravity habitats, advanced radiation shielding, hibernation or suspended animation to reduce metabolic activity and psychological strain. These ideas are not born of whimsy. They are responses to a very real problem. Time is the enemy. The longer the journey, the more it taxes the human system. And hibernation is a particularly telling concept. It suggests an admission that consciousness itself might be too costly to maintain for such long voyages, that the best way to protect the human body and mind may be to pause them, to step outside of lived time altogether. It is a radical idea, and one that remains speculative, but its very presence in serious discussions tells us how severe the challenge is. As we sit with these biological limits, as we acknowledge that propulsion and gravity assist can only take us so far, a new question quietly forms. If humans struggle with long durations, if our bodies impose a strict ceiling on how much time we can tolerate in deep space, then perhaps the problem is not how to go faster, but how much slower we would become if we refuse to use every available trick. What happens if we strip away gravity assists? If we choose simplicity over efficiency? If we send a spacecraft on a direct path, powered only by its engines, without borrowing speed from passing worlds? How much longer does the journey become? How much heavier does the burden grow? And in that stark comparison between assisted and unassisted travel, the scale of the challenge sharpens even further, setting the stage for the next step in understanding just how unforgiving the road to Neptune truly is. And so, once we have faced the limits of our own biology, once we have accepted that time itself presses differently on flesh than it does on machines, another question rises naturally to the surface. What if we made the journey simpler, at least on paper? What if we chose not to dance with the planets? What if we refused gravity's generous hand and set out on a direct path, relying only on our engines and our resolve? What if, we pointed a spacecraft toward Neptune and went straight there? At first glance, this idea feels appealing. There is a deep human instinct toward the straight line. The shortest distance between 2 points, we are taught, is a line. It feels honest, efficient, free of complication. No waiting for planetary alignments, no delicate flybys, no dependence on massive worlds moving on their own schedules. Just departure, acceleration, cruise, arrival, clean, simple. And yet, the universe has a way of punishing simplicity when it ignores context. In space, straight lines are deceptive. The moment a spacecraft leaves Earth, it is already moving sideways around the sun at tremendous speed. To go directly outward toward Neptune, You must fight that sideways motion. You must cancel it, redirect it, reshape it, and that requires energy, a lot of it. Far more than most people intuitively expect. If you do not use gravity assist, your spacecraft must carry nearly all the energy it will ever need from the moment it leaves Earth. There will be no borrowed momentum later. No planetary gifts. Every kilometer per second of speed must come from fuel you launch at the beginning. And as we have seen, fuel is not just fuel. It is mass. Mass that demands more thrust. More thrust that demands more fuel. The spiral tightens quickly. Let us imagine quietly what this means in practice. A spacecraft leaving Earth on a direct trajectory to Neptune would first need to escape Earth's gravity. That alone consumes enormous energy. Then it must reshape its orbit around the Sun, stretching it outward until it intersects Neptune's path. Without gravity assist, this stretch must be achieved almost entirely through propulsion. The result is a spacecraft that departs Earth much faster than Voyager 2 ever did, burning through fuel at a prodigious rate. Even with an optimistic chemical propulsion system, the achievable speed without assist is limited. You might reach a velocity that allows you to cross the distance to Neptune in perhaps 25 to 30 years, assuming everything goes perfectly. And that's the thing. That estimate already assumes best-case scenarios, lightweight payloads, and engines operating near their theoretical limits. Add real-world constraints, and the timeline grows longer still. Now consider ion propulsion. In theory, ion engines could eventually build up sufficient speed to make a direct journey competitive. But without gravity assist, the spacecraft must begin accelerating from a much lower baseline. Years would pass before it reached the kind of velocity Voyager 2 gained in a single planetary flyby. Those years add up. The cruise becomes longer. The exposure to radiation increases. The patience required stretches even further. There is also the problem of arrival. A direct trajectory often means arriving at Neptune at very high speed. Slowing down requires fuel. Without gravity assist to help manage velocity, the spacecraft may find itself unable to enter orbit, forced instead into a fleeting flyby or a complete miss. In some cases, mission designers may accept this. In others, it undermines the entire scientific goal. What emerges from this thought experiment is a stark contrast. Gravity assist is not just a clever trick. It is the difference between a journey measured in a decade and one measured in generations. Without it, Neptune retreats even farther into abstraction, its blue clouds slipping just beyond the horizon of what feels practically reachable. And there is a psychological dimension to this as well. A mission lasting 30 or 40 years challenges our ability to care. Funding cycles end. Priorities shift. People move on. A spacecraft launched today might not reach Neptune until long after the cultural context that created it has faded. The risk of abandonment grows. The silence lengthens. This is why direct trajectories are so rarely chosen for distant destinations. They are technically possible, yes. Physics allows them. But possibility is not the same as wisdom. The solar system offers tools to those willing to use them, and ignoring those tools comes at a steep price. There is also the matter of inefficiency. A direct path may feel shorter in a geometric sense, but it is often longer in time. This inversion of intuition is one of the great lessons of orbital mechanics. The path that looks longer on a diagram can be faster. The path that looks simple can be slow. In space, you do not travel through empty Euclidean space. You travel through a moving gravitational landscape. Imagine trying to swim straight across a river with a strong current. You aim directly for the opposite bank, but the water carries you downstream. To reach your target, you must aim upstream, following a curved path. The straight line fails. The curve succeeds. Gravity assist is that upstream aim. Remove it, and you are at the mercy of the current. Without gravity assist, the journey to Neptune becomes an exercise in endurance. The spacecraft must survive longer. Its systems must remain functional for decades. Its instruments must remain calibrated. Its power source must last. Every extra year is another opportunity for failure. The probabilities compound, quietly but inexorably. This is particularly sobering when we revisit the idea of human travel. A 30-year direct journey is not just challenging, it is nearly unimaginable. Even if propulsion could be made efficient enough, even if life support systems could be perfected, the human cost would be extraordinary. Generations would overlap. Crew members might spend the majority of their lives in transit. The mission would become less a voyage and more a moving world. isolated forever between departure and arrival. And that's the thing. When we strip away gravity assist, we reveal the true raw scale of the solar system. We see how much we rely on subtlety and patience to make exploration feasible. We see how thin the margin is between possible and impractical. This comparison also sharpens our appreciation for every minute saved by clever trajectories. Shaving 5 years off a journey is not a convenience. It is transformative. It reduces radiation exposure. It improves reliability. It keeps missions within the span of human attention and institutional memory. Gravity assist does not just make missions cheaper, it makes them psychologically and culturally viable. Yet even with all these techniques, even with gravity assists and hybrid propulsion, Neptune remains far. It demands years, it demands planning across decades. And this realization naturally leads us forward. If direct travel is too slow and assisted travel is still long, then perhaps the only remaining lever is technology itself. What if we could change the fundamental rules of propulsion? What if new engines could push us faster than anything chemical or ion-based systems allow? What if we could approach a fraction of light speed, not in fantasy, but in plausible engineering terms? How much would the journey shrink then? How would Neptune look if it were only months away instead of decades? As these questions begin to stir, as the contrast between assisted and unassisted travel settles into clarity, our attention shifts toward the horizon of possibility, toward ideas that sit just beyond our current reach. Nuclear propulsion, plasma engines, solar sails, concepts that promise not incremental improvement but a change of scale itself. And it is there, in that speculative but serious territory, that the story naturally continues, where imagination meets physics, and where Neptune becomes a test not just of patience, but of how boldly we are willing to rethink the way we move through space. And so, standing at the edge of what our current tools can offer, with gravity assists squeezed for all their elegance and conventional engines pushed to their practical limits, our thoughts drift naturally toward the future, toward ideas that feel less like refinements and more like leaps. Because if Neptune remains distant even after all our clever tricks, then perhaps the only remaining path forward is to change the very nature of how we move through space. This is where the conversation becomes speculative, yes, but not careless. These are not idle dreams. They are serious concepts, studied, modeled, debated by physicists and engineers who understand exactly how unforgiving reality can be. And, what they all share is a desire to break free from the tyranny of slow acceleration and limited exhaust speeds, to reach velocities that would fundamentally alter our relationship with the solar system. One of the most discussed ideas is nuclear propulsion. Not nuclear power as we use it on Earth to generate electricity, but nuclear reactions used directly to produce thrust. The promise here is simple and profound. Nuclear reactions release far more energy per unit mass than chemical ones. Orders of magnitude more. That extra energy could be used to heat propellant to extreme temperatures and expel it at much higher speeds, producing greater thrust efficiency. In practical terms, a nuclear thermal rocket could cut travel times to the outer planets significantly. Not instantaneously. Neptune would not suddenly be next door, but a journey that might take 30 years with conventional propulsion could potentially be reduced to perhaps half that. 15 years, still long, still demanding, but now approaching something that feels just barely within the arc of a human career. There is also nuclear electric propulsion, where a reactor generates electricity that powers ion or plasma engines. This combines the endurance of electric propulsion with the independence from sunlight that deep space demands. With such systems, a spacecraft could accelerate continuously for years, reaching speeds far beyond what chemical rockets can manage alone. The journey to Neptune might shrink further, perhaps to a decade or slightly more, depending on design choices. But nuclear systems bring their own burdens. Reactors must be shielded. Safety concerns loom large, both at launch and throughout the mission. Political and ethical considerations cannot be ignored. The engineering challenges are formidable, yet the physics is sound. The door is not closed. It is merely heavy. Then there are plasma engines, concepts that push electric propulsion to its limits. These engines manipulate charged particles using magnetic and electric fields, accelerating them to extraordinary velocities. The thrust remains low, but the exhaust speed is immense. Over long durations, the accumulated change in velocity could be transformative. Neptune could become reachable in times comparable to Voyager 2, but without the need for rare planetary alignments. Solar sails offer a very different vision. No propellant at all, just a vast, reflective surface catching the momentum of sunlight itself. Each photon carries a tiny push, almost nothing, but over time, it adds up. Near the sun, solar sails can accelerate steadily, building impressive speeds. The challenge is that sunlight weakens with distance. By the time you reach the outer solar system, the push becomes faint. Some proposals imagine diving close to the sun first, using intense sunlight to gain speed, then coasting outward on that momentum. It is an elegant idea, almost poetic. A spacecraft unfurling a sail, bathing in solar fire, then gliding silently toward Neptune. The travel times here vary widely depending on assumptions, but in optimistic scenarios, they could rival those of nuclear propulsion, though with far less control near the destination. And then, at the far edge of serious speculation, lies antimatter. The most energy-dense fuel imaginable. Matter and antimatter annihilate each other completely, releasing pure energy. In theory, an antimatter-driven engine could achieve exhaust velocities approaching the speed of light. In theory, Neptune could be reached in weeks or even days. But theory is a dangerous comfort. Producing antimatter is extraordinarily difficult. Storing it safely is even harder. Containing it for use as propulsion remains far beyond our capabilities. Antimatter is not a solution for tomorrow or even for the distant near future. It is a reminder of what physics allows, not of what engineering can currently deliver. Which brings us to the most tantalizing benchmark of all, a fraction of light speed, 1%, 5%, 10%. Numbers that feel small, almost modest, until you remember what they mean. At 1% of light speed, Neptune would be only a few weeks away. At 5% days. At 10% hours. And when you let yourself imagine that for a moment, something strange happens. Neptune shrinks. The solar system collapses inward. The vast distances that have dominated this entire discussion suddenly lose their power. Time itself bends to our will. But this vision comes at a cost so immense that it borders on the fantastical. The energy required is staggering. The engineering challenges verge on the impossible. The heat, the radiation, the stresses on materials, all push us beyond what we know how to manage. These speeds are not just about propulsion. They are about redefining our relationship with physics. At significant fractions of light speed, relativistic effects begin to matter. Time dilates, mass increases, navigation becomes more complex. Collisions with even tiny particles become catastrophic. The universe reveals another layer of resistance. So we are left, once again, in a place of humility. The future offers possibilities, yes, but not miracles. Every gain in speed brings new problems. Every shortcut opens a new set of constraints. Neptune resists being made easy. And yet, there is something profoundly hopeful in this exploration of future technology. It tells us that the distance to Neptune is not a fixed sentence. It is a variable, a challenge that shifts as our understanding deepens and our tools evolve. What seems unreachable today may feel routine tomorrow. Not because the universe changes, but because we do. Still, even the most optimistic projections remind us of a sobering truth. Faster engines do not solve everything. They reduce travel time, but they do not eliminate it. They lower some risks while amplifying others. They demand resources, infrastructure, and stability on Earth itself. A civilization capable of sending humans to Neptune quickly must first be capable of sustaining itself over long periods without collapsing. And that realization quietly redirects our attention once more. Because speed is only one part of the equation. Even if we could reach Neptune quickly, we would still need to survive the journey. We would still need food, water, oxygen, energy. We would still need systems that do not fail. The challenge shifts from how fast we can go to how well we can sustain ourselves while going. As visions of nuclear engines and solar sails fade gently into the background, another, more practical set of questions begins to surface. Questions about logistics, about supply, about what it truly means to support life or even machines on a voyage that stretches across the outer solar system. And in that shift, the story moves naturally onward, from propulsion to provision, from speed to survival, toward the quiet, complex problem of what it would actually take to live on the road to Neptune. And so, as visions of faster engines and radical propulsion systems slowly fade back into the realm of possibility rather than certainty, we are brought face to face with a quieter, heavier truth. Even if speed were no longer the dominant obstacle, even if Neptune could be reached in a fraction of the time we once imagined, the journey itself would still demand something far more difficult to engineer than thrust. It would demand sustenance, continuity, the ability to keep a fragile system alive, stable, and functional across an expanse of time and space that offers no forgiveness. You see, propulsion gets you moving. Logistics keep you alive. For a journey to Neptune, logistics are not a secondary concern. They are the mission. Food, water, oxygen, energy, waste, spare parts, psychological well-being, all of these must be accounted for from the very beginning. There are no supply ships, no emergency landings, no nearby outposts. Once you leave Earth, everything you will ever need must already be with you, or must be produced reliably along the way. Food seems simple at first. We eat every day. We know how much. Multiply by the number of crew members and the duration of the journey, and you have a number. But that number grows quickly. For a mission lasting decades, storing all food up front becomes impractical. It would dominate the mass budget. Packaging, preservation, spoilage, nutritional degradation over time all introduce complications. This is why long-duration missions inevitably turn toward recycling and production. Hydroponic systems, algae closed-loop agriculture, these systems are delicate. They require light, water, nutrients, careful balance. On Earth, ecosystems are resilient because they are vast and interconnected. In space, an ecosystem is small, artificial, and unforgiving. A single failure can cascade. A disease in a crop, a pump malfunction, a contamination, each one becomes existential. Water follows a similar story. Humans can survive weeks without food, but only days without water. Carrying enough water for decades is not feasible. Recycling becomes essential. Every drop must be reused, purified, reclaimed from waste. This has been demonstrated on space stations for months and years, but scaling it to decades without resupply, without replacement parts, pushes reliability to an extreme few systems on Earth ever face. Oxygen, too, must be generated and recycled. Carbon dioxide must be removed. Trace contaminants must be controlled. On Earth, the atmosphere is vast and self-regulating. In a spacecraft, it is a thin envelope, entirely dependent on machinery. The margin for error is measured not in percentages, but in minutes. Energy underpins everything. Lights, life support, propulsion, communication, computation. In deep space, solar power weakens dramatically. By the time you approach Neptune, sunlight is a faint whisper. Nuclear power becomes the only viable option for sustained energy production. Reactors must operate reliably for decades, without maintenance crews, without replacement fuel, without the possibility of shutdown and repair. They must be safe not only technically, but politically, ethically, and psychologically for the people living alongside them. Then there is waste. Every system produces it. Solid waste, liquid waste, heat. Managing waste is not glamorous, but it is fundamental. Waste that accumulates becomes toxic. Waste that cannot be recycled becomes a burden. Heat must be radiated away into space, which itself becomes more challenging as systems grow larger and more complex. Spare parts add another layer of complexity. Machines fail. That is not a pessimistic statement. It is a law of engineering. On Earth, we replace parts. In orbit, we improvise. On a Neptune mission, improvisation must be planned. Crews would need not just spare components, but raw materials, manufacturing tools, perhaps even the ability to print or fabricate parts on demand. The spacecraft becomes not just a vehicle, but a factory, a workshop, a habitat, a world. And this is where the scale of the challenge truly comes into focus. A mission to Neptune is not like a long flight or even a long sea voyage. It is closer to founding a small, isolated colony that happens to be moving. Every system must support every other. Failure in one domain propagates outward, threatening the whole. Psychological logistics are just as important. Humans need more than calories and oxygen. They need purpose, routine, meaning. Over decades, monotony can erode motivation. Isolation can magnify small conflicts into existential threats. Communication delays grow as the spacecraft moves outward. Conversations with Earth become asynchronous, stretched over hours. The crew must increasingly rely on each other, on internal culture, on shared goals that remain meaningful even as Earth becomes a distant memory. This is why some proposals include hibernation or torpor. Reduce metabolic needs. Reduce psychological strain. Reduce resource consumption. If humans could safely sleep through much of the journey, the logistical burden would shrink dramatically. Food consumption drops. Oxygen needs fall. stress diminishes. But this idea comes with its own uncertainties. We do not yet know how to safely induce and reverse long-term suspended states in humans. The risk is enormous. The promise is seductive. Cost looms over all of this. Every kilogram launched into space carries an enormous price tag. Every additional system adds complexity and risk. For a Neptune mission, costs would not be measured in billions, but in sustained national or even international commitments over generations. This is not something a single company or even a single country undertakes lightly. And yet, there is a strange parallel here, one that speaks quietly to people on Earth, especially those in their working years, navigating long-term goals with uncertain payoffs. A journey to Neptune is a lesson in delayed gratification. You invest now for a return far in the future. You must plan carefully, diversify risk, build resilience, accept that not everything is under your control. Perhaps that is why the idea resonates so strongly with people in their 20s and 30s. Building a career, saving for the future, investing in skills, managing health. These are all long journeys, not unlike a voyage to Neptune. Short-term sacrifices made in service of distant goals. Systems built to endure, not to impress. The logistics of reaching Neptune force us to think like that. Not in terms of quick wins, but in terms of sustainability. Not in terms of heroic moments, but in terms of quiet reliability. The most important systems on such a mission would not be the engines or the antennas. They would be the ones that simply keep working, day after day, year after year, unnoticed until they fail. And this brings us, almost inevitably, to a broader perspective. Because once we have accounted for speed, propulsion, biology, and logistics, we begin to see that there is no single answer to how long it takes to reach Neptune. There are only scenarios. Each one a different balance of time, cost, risk, and ambition. What if we launch at the perfect moment, using gravity assist and conventional propulsion? What if we accept a longer journey in exchange for simplicity? What if we bet on future engines? What if we send machines only? What if we send people and accept the cost? Each scenario produces a different timeline, a different story, a different meaning. And so, having assembled all the pieces, having explored the constraints and the possibilities, our minds naturally turn toward comparison, toward laying these scenarios side by side and asking not which is fastest in theory, but which is most realistic, which aligns with who we are now and who we might become. In that comparison, the abstract question of travel time transforms into something richer. A map of choices. A set of paths branching outward, each leading to Neptune by a different route, each carrying its own implications. It is there, in that quiet act of comparison, that the journey enters its final phase, where numbers become narratives, and where the many ways of reaching Neptune reveal as much about us as they do about the distant world waiting in the dark. And so, with all the pieces now laid out before us, speed, propulsion, gravity, biology, logistics, the abstract question finally begins to crystallize into something more tangible. Not a single answer, but a spectrum of possibilities, different paths through the same cosmic landscape, each shaped by a different set of choices. And, this is where the journey to Neptune stops being a thought experiment and starts to resemble a set of lived futures, branching quietly away from one another. Imagine first the most conservative, most proven path, a spacecraft launched at precisely the right moment, when the geometry of the solar system opens a narrow corridor outward. It leaves Earth riding the brute force of chemical propulsion, escapes the planet's grip, and then begins a carefully choreographed dance with the giants. Jupiter lends its immense energy, bending the trajectory outward. Saturn refines the path. Perhaps Uranus offers a final nudge. The spacecraft coasts, accelerates without burning fuel, and arrives at Neptune in something like 12 to 15 years. This is the Voyager-style journey. Elegant, efficient, demanding in planning but modest in technological risk. It is slow by everyday standards but fast by cosmic ones. It fits within institutional memory. It produces data while the people who designed the instruments are still alive to interpret it. This scenario feels realistic because it has already happened, at least once. Its weakness is rarity. The launch windows are infrequent. Miss one and the whole timeline shifts by decades. Now imagine a similar mission, but without the generosity of gravity assist. The same chemical propulsion, the same departure from Earth, but no planetary handshakes along the way. The spacecraft must rely on its own fuel to reshape its orbit around the Sun, stretching it outward toward Neptune. The result is a longer cruise, 25 years, 30 years, perhaps more, depending on payload and engine performance. This path is simpler in concept, but harsher in consequence. More fuel at launch, more mass, more stress on systems, a longer exposure to radiation, a greater chance that something somewhere will fail. This scenario is technically feasible, but it feels heavy. It asks for patience without reward. It tests not just engineering, but commitment. Then there is the hybrid approach. Chemical propulsion to leave Earth, gravity assist where available, and ion engines humming quietly in the background for years. This spacecraft does not rush, it does not sprint. It builds speed gradually, almost imperceptibly, day after day. The ion engines add kilometers per second not in dramatic bursts, but in steady accumulation. Over time, the difference becomes significant. A journey that might have taken 20 years shrinks to 15. One that might have taken 15 shrinks closer to 10. This scenario feels like a bridge between worlds. It uses what we already know, while stretching toward what we are still mastering. Its success depends on endurance, on power systems that do not fail, on navigation that remains precise across millions of kilometers and millions of seconds. Solar sails offer a different flavor of realism. A spacecraft unfurls a vast reflective sheet and lets sunlight do the work. Near the sun, the acceleration is gentle but persistent. Over time, speed builds. The sail catches momentum from photons that have traveled millions of years only to end their journey with a tiny push. If the trajectory is designed well, the spacecraft can reach the outer solar system with respectable velocity, perhaps in a time comparable to ion-driven missions. 10 to 20 years, depending on assumptions. The beauty of this scenario lies in its simplicity. No fuel, no exhaust, just light and patience. Its weakness lies in control and in the diminishing strength of sunlight. Neptune is far from the sun. The sail must do most of its work early, then coast for a long, silent stretch. Now let us turn our attention to nuclear-powered missions. Here, the timelines begin to contract more noticeably. A nuclear thermal rocket could push a spacecraft onto a faster trajectory from the start, reducing travel time to perhaps 10 to 12 years, without relying heavily on gravity assist. Nuclear electric propulsion could run powerful ion or plasma engines continuously, adding speed steadily across the entire journey. In optimistic scenarios, Neptune might be reached in 8 to 10 years. This is a profound shift. A destination that once demanded a generation now fits within a decade. The cost is complexity, safety, politics, trust. This scenario asks not just for engineering excellence, but for societal agreement that such missions are worth the risk. And then there are the speculative extremes. Advanced plasma engines, fusion-based propulsion, concepts that promise exhaust velocities so high that the traditional limits of space travel begin to loosen. In these futures, Neptune could be reached in 5 years, perhaps even less. The journey becomes short enough that human presence starts to feel conceivable, at least on paper. But these scenarios rest on breakthroughs that have not yet arrived. They are visions rather than plans. They tell us what might be possible, not what is likely. At the outer edge of imagination lie the fractional light-speed dreams, 1%, 5%, 10%. In these worlds, Neptune is no longer distant. It is weeks away, days away. The solar system collapses inward, transformed from a vast wilderness into a navigable neighborhood. But these scenarios are almost parables. They exist to show us the ultimate ceiling imposed by physics, not the floor of practicality. The energy requirements are staggering. The risks are profound. The engineering hurdles remain unsolved. They inspire, but they do not yet instruct. What emerges from laying these scenarios side by side is not a single answer, but a pattern. Every reduction in travel time comes with an increase in cost, complexity, or risk. There is no free victory. Faster journeys demand more from us, not just technologically, but culturally and ethically. Slower journeys ask for patience and resilience. Each path to Neptune reflects a different version of who we are willing to be. There is also a quiet truth hiding here. For robotic missions, longer timelines are acceptable. Machines do not mind waiting. They do not age. They do not grow restless. A 30-year journey is an inconvenience, not a tragedy. For humans, time carries weight. A decade is significant. 2 decades is transformative. 3 decades is a lifetime. This difference alone shapes which scenarios feel plausible for which kinds of explorers. If the goal is knowledge, then the slower paths remain valid. A carefully planned robotic mission, launched at the right moment, using gravity assist and efficient propulsion, can reach Neptune and return data that reshapes our understanding of the solar system. The wait is long, but the reward is lasting. If the goal is presence, if we imagine humans someday standing beneath Neptune's distant sun, then the faster, more radical scenarios become necessary, even if they are far from ready. And perhaps this is the most important insight of all. The question, how long does it take to reach Neptune, has no single answer, because it is not really a question about distance. It is a question about priorities, about what we value, about how much we are willing to invest for how long, and for what kind of return. In one scenario, Neptune is a destination for patient machines, reached quietly over decades. In another, it is a proving ground for advanced propulsion, reached within a single career. In yet another, it becomes almost mundane, just another waypoint in a solar system made small by extraordinary speed. Each scenario is internally consistent. Each is grounded in physics, and each tells a different story about humanity's relationship with time and ambition. As we stand here surveying these branching paths, it becomes clear that the journey to Neptune is not just about getting there. It is about what the journey demands of us along the way. The planning, the waiting, the persistence, the willingness to commit to outcomes we may never personally witness. And in that realization, something shifts. The technical comparisons begin to fade into the background, replaced by a quieter, more reflective question. Why do we care so much about this distant world? What is it about Neptune, cold and remote, that draws us into such elaborate calculations and long-term dreams? Perhaps the answer lies not in Neptune itself, but in what it represents. The farthest edges of the known, the challenge that resists shortcuts, the reminder that some goals cannot be rushed without losing something essential. And as that thought settles, as the many scenarios converge into a single sense of meaning, the journey naturally approaches its final reflection, where Neptune becomes less a destination and more a mirror, reflecting back our limits, our ingenuity, and our quiet, persistent desire to go just a little farther than before. And so, as all these paths converge in our minds, something subtle but profound begins to take shape. Neptune, that distant blue world we started with as a question, slowly transforms into something else entirely. It becomes less a destination and more a measure, a ruler held up against our capabilities, our patience, our values, because when you strip away the equations, the propulsion systems, the carefully timed flybys, what remains is a single, enduring truth. Neptune is far not just in space, but in meaning. You see, Neptune sits at the edge of our practical reach. Not the edge of imagination, but the edge of what we can realistically touch with today's tools and today's way of thinking. It is close enough to tempt us, to whisper that it might be possible, yet far enough to punish arrogance, to expose shortcuts, to remind us that the universe does not yield easily. And that's the thing. The journey to Neptune asks us to confront our limits honestly. It tells us that speed alone is never the full answer. We can go faster, yes, but only by paying a price. More energy, more risk, more complexity. It tells us that strategy matters more than brute force. A carefully chosen trajectory can outperform raw power. Timing can matter more than thrust. Patience can be a form of intelligence. It also tells us something deeply human, that long journeys reveal character. A mission to Neptune is not won at launch. It is won in the quiet years that follow, in the uncelebrated work of monitoring systems, in the discipline of maintaining focus when results are decades away, in the humility to accept that the people who begin the journey may not be the ones who finish it. This is why Neptune feels different from Mars or the Moon. Those worlds invite urgency. They invite near-term goals. Neptune invites reflection. It asks whether we are capable of thinking in spans longer than our own lives, whether we can build institutions, cultures, and commitments that outlast individual ambition. And when you think about it this way, the technical question, how long does it take to reach Neptune, becomes almost secondary. The deeper question is whether we are willing to accept what that time represents. Years of waiting, years of uncertainty, years of effort whose reward may be knowledge rather than presence. Neptune also reminds us that the universe does not owe us accessibility. Some places are distant because they are meant to be earned, not through conquest but through understanding. The slow accumulation of insight, the willingness to listen to what physics allows rather than what we wish it would allow. There is a quiet beauty in that, A reminder that exploration is not always about planting flags or claiming territory. Sometimes it is about sending a small, fragile machine across billions of kilometers simply to look, to measure, to learn. Voyager 2 did that. It did not conquer Neptune. It greeted it briefly, respectfully, and moved on. And perhaps that is the lesson Neptune offers most clearly. That not every journey needs to end with arrival. Some journeys exist to teach us how to travel, how to plan, how to wait, how to cooperate with forces far larger than ourselves. In that sense, Neptune mirrors many of the longest journeys we take in our own lives. Building expertise, raising a family, creating something meaningful. These are not sprint goals. They unfold slowly. They resist shortcuts. They reward consistency more than intensity. The path matters as much as the destination. For those in the middle of their lives, in their 20s and 30s, navigating careers, finances, identities, Neptune offers an unexpected metaphor. It says that distant goals are not unreachable, but they demand alignment. Of timing, of resources, of effort sustained over years. It says that progress is often invisible day to day, but unmistakable when viewed across a decade. And this may be why Neptune continues to draw our attention, even though it offers no easy victories. It stands as proof that there are still places that require us to grow before we can reach them. That challenge us not just technologically, but culturally. As our engines improve, as our understanding deepens, Neptune will not move closer, but we might, slowly, carefully, with respect for the scale of what we are attempting. Whether that journey takes 12 years, 20 years, or far longer, the act of attempting it reshapes us. And so, the silence of Neptune is not emptiness. It is an invitation to think longer, to plan better, to accept that some doors open only when approached with patience. Somewhere out there, beneath a faint and distant sun, Neptune continues its slow orbit, indifferent to our debates, untouched by our timelines. It waits, not for us specifically, but for the moment when our curiosity, our technology, and our willingness to endure align once again. And when that happens, the journey will not just be about reaching a distant planet. It will be about proving that we can listen to the universe, move with it rather than against it, and carry meaning across the vast, quiet spaces between worlds.